This video is on the ideal and combined gas laws. So we talked about in the previous video about the basic gas laws of Boyle's law, Charles' law, and Avogadro's law. When we wrote the laws, we wrote them equal to volume, and then we had a constant, K, B, and A, that helped us give a relationship between volume and our different variables, so volume and pressure, volume and temperature, and volume and moles. If we were to combine all of these constants together into one constant, that constant is formally called R. R is the universal gas constant. R is derived from the ideal gas law at standard temperature and pressure conditions. Looking at the R value, or the universal gas constant, when we have ATM as our pressure units, we get a value of 0.08205 ATM liters per mole Kelvin. Like I said, this comes from our ideal gas law. Our ideal gas law we refer to as PIV-NERT, PV equals nRT, PIV-NERT, where my pressure can be any one of my pressure units so long as the pressure units on R match up with the pressure units given to me. My volume has to be in liters, N is moles, and T for temperature has to be in Kelvin. So note that units on pressure must match the pressure units on R. Our R value units, if we were to arrange our ideal gas law constant for R would be equal to PV over NT. And my R units on R are equal to ATM liters per mole Kelvin. And we can see that rearranging this equation for R, our variables line up with our units. And so if we were to say that we had 1 atmosphere, our 22.4 liters, our 1 mole, and then our 273 Kelvin, when we go ahead and multiply and divide those, that's where we get these numbers from. So we can get an R value for atmospheres, we can get a constant for millimeters of mercury, for torr would be the same because they're the same units, for kilopascals. So we really just need to know the ideal gas law and then the combined gas law. We don't have to remember all those little gas laws, Boyle's, Charles, Gay-Lussac's, and Avogadro's, because they all come from the combined gas law. So depending upon which constants are constant, which variables are constant, we can derive each one of our laws from that. So if we have constant temperature and moles, that means that if they're constant, they're the same on both sides, so they cancel out. I'd be left with P1 times V1 equals P2 times V2, which is Boyle's law. If I have constant pressure and moles, that means that they'd be the same on both sides, so they would go away. And then I'd be left with V1 divided by T1 is equal to V2 divided by T2, which is Charles' law. Furthermore, if I have constant temperature and pressure, so temperature and pressure being constant here, pressure and temperature being constant here, I'm left with my volume divided by my moles for both situations, which is Avogadro's number. So long as we know which variables are being held constant, we can derive all of our equations when variables are changing from one condition to another from the combined gas law. We should note that most gases behave ideally at pressures less than 1 atmosphere and very high temperatures. Here we assume that molecules have no volume or interactions. So we say their interactions are elastic. So there's no forces given to either molecules when they interact. Let's go through a couple example questions. So our first example is looking at how many moles of gas are present in 8.56 liters of a sample of hydrogen gas at 0 degrees Celsius and 1.5 atmospheres. Anytime we see that we're asked to find moles we know is N, and that's our giant red flag that tells us, hey, use your ideal gas law. I first go ahead and pull out my variables given to me. I have a volume of 8.56 liters. I'm told I have hydrogen gas at 0 degrees Celsius, which I know that I need to convert Celsius into Kelvin by adding 273. And I have a pressure of 1 atmosphere. I'm asked to find moles, so I record that, and that gets an exclamation or a question mark, because that's what I'm looking for. And then I have to choose my R value. Because I have units of ATM, my R value is going to be my 0.08205 atmosphere liters per mole Kelvin. Then I go ahead and write my formula, and I am looking for moles. So if I'm looking for moles, I divide away what I don't want on either side, which is RT. Therefore, moles, N is equal to PV over RT. From there, I plug in my values, my 1.5 atmospheres, my 8.56 liters, my R value, ATM liters per mole Kelvin, and my temperature of 273 Kelvin. Now I know my equation's set up correctly because my units cancel out except for moles. So atmospheres here cancels out with atmospheres here. My liters here cancel out with my liters here. Within my bottom part, Kelvin's on top in my 273 and Kelvin's on the bottom here, so those cancel out. And I'm left with 1 over moles. So 1 over a fraction is just moles. So I'm left with my units of moles, so I know that this is set up correctly. When I plug this in, I get 0.57 moles of hydrogen gas. Now our next equation gives us two different situations, an initial and a final situation, and we're asked to find the new volume of methane. So given that we start with 3.8 liter sample of methane at 5 degrees Celsius is heated to 86 degrees Celsius. So my starting volume, my V1, is 3.8 liters. My initial temperature is 5 degrees Celsius, which I convert to Kelvin to get 278 Kelvin. My final temperature of 86 degrees Celsius is converted to Kelvin to give me 359 Kelvin. And then I use my combined gas law. So because both pressure and moles are not being told to me, I assume that they're being constant. So it means pressure and moles are the same for both sides, so they drop out of my equation, which means I now have V1 over T1 is equal to V2 over T2. I'm looking for V2, so I can cross multiply or bring my T2 up. So V2 is equal to V1 times T2 divided by T1. Plugging in my variables, my 3.8 liters, my second temperature of 359 Kelvin, and my initial temperature of 278 Kelvin, I get an answer of 4.9, and my units, I have Kelvin and Kelvin, so I'm left with liters, so 4.9 liters of my methane. In my last example problem, I have more variables that are changing. I have a 3.48 liter sample of B2H6 at negative 15 degrees Celsius and 354 torr. It needs to be moved to a new container to create a pressure of 468 torr and 36 degrees Celsius. What is the volume of the new container? Well, first off, I have my volume of my initial volume of 3.48 liters. My initial temperature is negative 15 degrees Celsius, which I convert to Kelvin, and that gives me 258 Kelvin. My initial pressure is 354 torr. I'm looking for my new volume. My new temperature is 36 degrees Celsius, which in Kelvin is 309 Kelvin, and 468 torr. Again, just like before, I can write my combined gas law. And from there, I know that my moles are not changing because they're not told to me in the problem. So those cancel out. So that means I'm left with P1 over V1, or P1 V1 over T1 is equal to P2 V2 over T2. I'm solving for V2. So I cross multiply, my T2 comes up and my P2 comes down. So my new volume is equal to P1 V1 T2 divided by T1 P2. When I plug that in, my V2 is equal to my initial pressure, 354, times my initial volume, 3.48, times my new temperature of 309, divided by my initial temperature of 258 and my new pressure of 468. Now it's important when you plug this in your calculator that you multiply these together and you divide by the product of these two multiplied by each other. Okay, if you just hit divide by this times that, you're going to get the wrong answer because that's the wrong order of operations. When I plug those in, I get 3.07 liters of diboron hexahydride.